Welcome, good afternoon, everybody, and welcome to today's Quantep seminar. This is the last seminar of the year, and it's a pleasure for me to introduce you, Martin Savage. He's a professor of physics at the Institute for Nuclear Theory at the University of Washington. He studied at Oakland, got his PhD at Caltech, and in the last years has been worked and focused his activity in applying quantum computing and quantum information theory to problems in nuclear and high energy physics. And today he will present us some of the last results he got. And I am very, very eager to listen to his news. Please, Martin, the floor is yours.
Thank you very much, Simone. So let me arrange things here. So thank you very much for the invitation to speak here. It's an honor, and thank you for the nice introduction. I'm going to do something a little bit different today. I'm going to tell you my thoughts on quantum computing for quantum field theories and nuclear physics. And focus on some of the results, but also some of the conceptual developments and thoughts that have been evolving over the last couple of years. And I wish to point out at the beginning that a lot of my thinking has been shaped by long discussions with Natalie Clough and Alessandro Ruggiero. So we're in this really remarkable period. And during the last 5 years, we've seen really two major disruptive changes, not only in computing, but also entering the domain sciences rapidly. One is artificial intelligence and machine learning. The other is quantum computing and quantum simulation. And of course, these are not independent developments. There's significant overlap between them. But they're really changing. It's an interesting period in time where they're really changing our capabilities for making advances in the research programs in the domain sciences, for instance, high energy physics, nuclear physics, materials. And really, we're just only at the beginning of understanding and contemplating where these may take us. Excuse the beep. So I'm not going to talk about the machine learning and artificial intelligence. I'm far from an expert. I will be talking on the quantum simulation related to high energy physics and nuclear physics. More generally, before we get there, if you look at the impact of quantum information science, quantum computing, where some of the thrusts are and where it's taking us, there's really three areas roughly where the progress has been truly spectacular. One's in quantum computing simulation. We've seen in the last couple of years the first quantum advantage, where a quantum computer has outperformed a classical computer. This, of course, was built upon decades of development at universities and national labs and technology companies, and is one of a number of platforms that have really been that have demonstrated great progress for moving forward. This one was a superconducting qubit system from Google, 54 qubits, and it performed a computation in about 3 minutes that the fastest classical computer takes a couple of days to perform. And so one can only speculate, and progress is of course happening already, has been reported more recently as to how this moves forward or accelerates forward. Another one is in communication, and there's been progress internationally, of course, to stand up quantum internets for the reasons that we're all aware of. And here's a report from earlier in the year, January, describing the Chinese efforts in quantum communication, describes multi-optical element network, including satellites, telecommunication, infrastructure with QKD distributed over about 4,500 kilometers. And then also in quantum sensing, the advances with cold atom systems and other systems, but with cold atom systems is what I've have this a picture of from just a month ago. One uses the interferometry of matter to be able to perform, in efforts to be able to perform navigation and location with high precision, and also in the absence of, say, GPS. So with regard to the potential of quantum computing and quantum simulation for physics, this is was identified in the early 1980s, and in fact the title of the slide could in fact have been I should have paid more attention in graduate school. And as was pointed out in the papers by Feynman, Benioff, and others, with a summary essentially of you can't describe a more fundamental theory in terms of a less fundamental theory. The limitations of classical computing and classical simulation were identified, and really during the last 5 or so years, where with the emergence of exascale computing and the planning for exascale computing, it was pretty clear at that point that classical computing was not going to be able to address the problems that we have in high energy physics and nuclear physics and even materials. The great thing, of course, that was also described in these papers is the fact that quantum mechanics works the same at all scales. And so for our problems, for instance, high energy physics at sub-Fermi length scales, and say nuclear astrophysics, where you're looking at cosmological length scales, then quantum mechanics operates the same in both of those regimes. And as a result, if one can be clever, then one can map those problems onto quantum devices that sit, say, in a room or on a desktop, excuse me, and perform the operations allowed by quantum mechanics, unitary operations, measurements, to perform faithful simulations of those systems on a different quantum system. The new element, of course, here, or the new elements are entanglement and coherence. The rapid progress in the laboratory for the controlling entanglement and coherence led to the first devices available for simulation on the cloud 5 years or so ago, 2017, 2018. And so now for the last few years, many of us, everybody in the audience, have been accessing these devices or designing these devices relevant for scientific application. And so the questions still remain, how does one include the quantum simulation, future quantum simulation, quantum computing and communication capabilities into the computing environment and the computing ecosystem that we have in order to advance calculations and predictive capabilities of the standard model. So, of course, one of the questions that's high on everybody's mind is where do we find a quantum advantage for scientific application, in particular standard model physics. And so this is a really important question for us to be dwelling on and thinking about. There's no right answer here at the moment that's obvious. And really a lot of the thinking that I'm going to be talking about today has emerged from contemplating this question. So if a classical computer can solve the problems that you're interested in, then there is no reason to seek a quantum device. It would be a highly inefficient way and complicated way to solve a problem that one can solve potentially on your laptop or on a supercomputer. So the utility then of quantum devices is to solve and address the parts of the problem that you can't solve with a classical computer. And what that means is that we have to know our problems well, and we have to know our problems better than we do today. So we need to understand and take time from both a theoretical and numerical point of view to understand the entanglement structures and dynamics of the systems of interest. It's important to keep in mind, of course, in doing this, that the quantum devices that one can envisage are all embedded in large-scale classical computing environments. So in some sense, the classical computing is not going to be the limitation for the pieces that are amenable to classical computation. it's the pieces that are that we really have to identify the pieces that have to be done on a quantum device, and then one has some sort of a hybrid architecture where those pieces are pushed onto the QPUs, for instance, and then brought back and stitched together on the classical computing components. So I listed just a number of the targets, if you like, in the standard model that for quantum simulation, and essentially everybody in the audience knows where we are challenged computationally. If you looked at the exascale resource requirements that were established around 2016, 2017, then the really large resource requirements were going to problems that fell into a couple of classes. One is real-time dynamics or non-equilibrium dynamics of systems, and the other is finite density systems, dense matter, or nuclei, for instance. And so in Hanji physics, one can imagine asymptotically having computations that take us from the initial state all the way through the collision process to the final state, where this is, of course, a highly inelastic process. We're not close to performing such calculations. We don't yet understand the complexity class of these problems and how they're going to scale going forward. There's been nice models, toy models that have been executed both on simulations and on simulators, which indicate that there really is going to be value in pursuing such calculations, particularly the quantum coherence, as you move through the fragmenting process. And so this is not just for asymptotically high energy collisions. This applies throughout all of inelastic collision processes, or even just elastic collision processes, including, for instance, neutrino nucleus breakup. So also moving along those in that same class, if you like, as low energy nuclear reactions and fission, the electroweak processes on nucleons and nuclei, as I mentioned, for instance, for neutrino nucleus breakup, and also the dynamics of neutrinos in extreme astrophysical environments, such as in supernova. In the other class, the finite density, so it's well known that in finite density problems, most of them, one encounters a sign problem in stochastic evaluation of the path integral in Euclidean space. This is because the chemical potential in Euclidean space has an associated I associated with it. And so in evaluating the path integral, you have a phase that above certain mass relations, one has a phase that spins around in such a way that stochastic sampling is not convergent. Of course, one can go so far with such calculations. You can obtain results with error bars on them, but to reduce the precision further requires exponentially growing classical compute resources, and so it's not really practical. It's not a practical path forward for arbitrarily reducing the uncertainties. And so the expectation is, because working with a Hamiltonian formulation, the chemical potentials don't have this nasty I associated with them, that quantum computing is going to be address the finite density problems. The expectation is that, of course, that is the case. However, we still don't have a deep understanding of which of the sign problems will be addressable with quantum computing and which won't. And the last bullet that I have here on my list is precision structure interactions of medium and light nuclei. So to do a full configuration calculations of the states and dynamics of light nuclei, this is an exponentially growing Hilbert space with regard to the number of bodies. And so this is a type of computation that's particularly well suited for quantum devices, and is challenging, of course, for classical devices in an obvious way. So let me just step back a bit and talk about a couple of things that are obvious, but it lines up well with some of the thinking that we have on entanglement for quantum field theories and the utility in quantum simulation. So imagine that I have a state denoted by this nice set of bubbles, say a pure state, and one selects two regions, regions A and B. And if you can write the density matrix as a sum of probabilities times tensor products of the density matrix in A and the density matrix in B, then the system is separable. That is, there's no sets of local operations and classical communications that will reveal quantum correlations between regions A and B. Now, it's interesting to think about this a little more because it's directly relevant, as I mentioned, to quantum antibody systems and quantum field theories. But now, a long time ago, 1995, there was first highlighted this interesting feature in the context of the Werner state. So if I have a density matrix which depends upon the probabilities eta, and it corresponds to a mixed ensemble where there's some probability of being in a entangled state, the 0, 0 plus 1, 1 state, plus just an isotropically distributed component for the rest of it. One can write that same density matrix as a linear combination of density matrices of the following form written down here, which are classically correlated. They're all tensor products. And so as a result, if all of the coefficients of in the second expression for the density matrix are positive, and of course, sum to a number less than 1, then that's a viable density matrix for the system. Now, it turns out, if you look at the last term with this 1 minus 3 eta sitting in front of the 0, 1 and the 1, 0. So if in order for this to be a valid decomposition, then that number also has to be positive. So if eta is less than 1/3, then in fact, that's a valid density matrix to describe this system. Excuse me, which is the situation I was describing previously. That is, it's an entirely classical one. There's no quantum correlations to be identified. On the other hand, if eta is bigger than 1/3, that is, there's in the upper density matrix, it's starting to be increasingly dominated by the entangled pairs. Then in fact, it can't be written like this. So if you're in the situation where you've created the state where the Bell pairs with these entangled states and the isotropic identity matrix component, and eta is less than 1/3, then you can't tell that there's quantum correlations in there. And the system is separable, but it contains entanglement. And so this is exactly the situation that we have in field theory. And sort of adding on top of that now, looking at three particle or three region entanglement or separability. You can imagine a situation where you have A, B, and C, and if you can imagine where A and B are separable, A and C are separable, and B and C are separable, but when you join A and B together, that it's not separable from C. And even in the simplest of quantum field theories, this is a situation that you find. So pulling out subregions of, for instance, the vacuum of quantum field theories and looking at whether and asking the question whether it's separable enough is not sufficient to tell you the actual structure, and which means it's not sufficient to tell you what you have to put onto the quantum device. So before I continue along that path, let me go back and just have a slide on perspective. So if you think about what was happening in the 20th century, the development is an absolutely remarkable period in history of theoretical physics, the establishment of quantum field theories and so forth. And the last part of the 20th century was really spent identifying and verifying short distance fundamental interactions, the standard model, QCD, for instance. And so the perturbative tools and effective field theories for handling the standard model were developed, but also the non-perturbative techniques, lattice QCD, was developed to the precision tool that it is today, utilizing high-performance classical computing. And during that period, the modeling, the hadronic modeling of starting in before the 1970s, in the 1960s, and all the way through to when QCD was accepted to be the correct Hamiltonian description, the hadronic modeling and modeling in general gave way to effective field theories where one identified Lagrange densities, small expansion parameters, and renormalization and regularization and renormalization techniques that provided systematic expansions of the observables of interest. So during this period, typically, if you looked at the effective field theories that have been successfully applied, the leading order in these theories is unentangled. So, for instance, in heavy quark effective field theory, when the leading order describing a B meson is a heavy quark tensor producted with some light degrees of freedom. Now, the light degrees of freedom are just denoted by their quantum numbers. One doesn't ask any deeper questions than that, but that's sufficient to provide predictive capabilities for particular observables in heavy quark systems. And then, of course, in the lattice QCD calculations then allow you to do high precision calculations for the other observables that are not protected, for instance, by the symmetries of heavy quark effective theory. And then also, in addition to that, which is relevant for our discussion, is that effective field theories were developed specifically to connect lattice QCD calculation simulations to nature. So, for instance, quenched and partially quenched effective field theories for the low-lying hadrons were developed, both finite volume calculations, finite lattice spacing calculations were developed, and each of these is essential, less so the quenched and partially quenched, but each of these is essential for making connections between the simulations and experiment. And this is going to remain the case for quantum simulations, which will be performed at finite lattice spacings and finite volumes. Different systems, but basically the same. So in the nuclear physics side of things, while the effective field theories and standard model were being developed in high-energy physics, one of the important developments was controlling the short range interactions of the nuclear force. Until about even into the 1970s, 1980s, the strength of the short range repulsion was incompatible with the quantum many-body techniques available at the time, which meant that it was not possible at that time to provide reliable computations in a systematic way. This changed with new tools coming in from outside communities, tools from high-energy physics, quantum chemistry, materials were brought to bear on the nuclear physics problem, and particularly the renormalization group and effective field theories changed the situation to the point where it is today, where one has nuclear forces and interactions, effective ones, that are systematically connected through global symmetries to QCD that can be used with quantum many-body techniques, the modern ones, to provide systematic predictions. In the United States, this was enabled through a number of avenues, but one of them with the SIDEC projects coming out of the Department of Energy that brought together applied mathematicians, computer scientists, nuclear physicists, particle physicists together. And so now, as we look towards as we're in the 21st century and we look towards the emergence of quantum computing, quantum simulation for standard model physics, nuclear and particle physics, we have to, the focus is going to be on understanding entanglement and coherence in the context of our simulations and the effective theories and the tools required to connect those simulations to make predictions for experiment. And so the thinking that we have had in the 20th century changes now to a conscious consideration of the entanglement structure, as I mentioned earlier, and how do we actually use the entanglement structure to design the mappings, for instance, and how we perform time evolution and so forth going forward. I want to say some words about complexity, just one slide. So the complexity is typically something in HEP and NP that we haven't worried about too much with regard to classical computing. And so far that hasn't been a problem for us. But there's some value in a more deliberate consideration. So the complexity class, if you like, that a problem sits in defines the scaling of compute resources required for asymptotically large systems, as you scale the size of the system. So if you're in a very large system and you double the size of the system, the question is, how do the computing resources scale? And from the quantum information side, there's been some really impressive results obtained, and they're shown in this diagram here on the left. So for instance, we know that finding the ground state of a K-local Hamiltonian in general is QMA complete. We know that the time evolution of a quantum system is BQP. That is something that can be performed efficiently on a quantum computer. And we also know that lambda phi 4 theory, interacting scalar field theory, is BQP complete. This was a result obtained in some beautiful papers by Jordan, Lee, and Preskel. And what that means is that any problem that can be solved on a quantum computer can be mapped with polynomial resources onto interacting scalar field theory in the presence of classical sources. But it also should be mentioned here that the complexity class defines the worst case scaling, or the scaling of a general problem. And there are certainly examples, and I'll give one in a minute, where particular choices of the coupling constants in a Hamiltonian mean that the actual scaling of solving that problem doesn't scale. It scales, for instance, in BQP, even though naively for arbitrary sets of couplings would sit out in QMA. And it's also the case, as the quantum chemists have taught us, is that just because something is scaling polynomial of the resources doesn't mean to scale doesn't mean to say that for the near-term devices and the calculations we're going to be doing in the foreseeable future are easier than if it's scaled in a different complexity class. So for instance, polynomial to the x to the power of 10 is worse than e to the 0.01x until about x is 9,000. So it's conceivable that asymptotically problems that we want to address are basically scaling exponentially bad and will provide a limitation. But in general, there's a long way to go through the near term and near future term devices, and even potentially, say 20 years down the road before one actually encounters that as a barrier. It's also interesting that the BQP, the B is an important letter here, the bounded, because as soon as one's considering bounded computation, that means you're actually free to change all of the elements of the computation, including the Hamiltonian that you're simulating, to within small tolerance, as long as at the end of the day, the result of the computation, both statistical and systematic, lies within the target epsilon. And in fact, this boundedness on the classical side is being used extensively to solve problems that are different but close enough to keep the error within some small epsilon. And so with some target precision, one has essentially a lot of freedom in even choosing which problem that you solve on the quantum device. It's known, as was discussed and discovered, more than 20 years ago, that by Seth Lloyd, that the time evolution of the quantum systems is something that's BQP, and is something that can be addressed with quantum devices with polynomial scaling resources. And this is true for both bosons and fermions. The thinking, of course, is that, and it is the case that if one has a quantum system with n degrees of freedom evolving for some time period t, this requires a simulation of n degrees of freedom evolving through n time steps, that where n times the time step takes you through the time evolution. And as I mentioned, even for fermions, it's still polynomial scaling in the number of degrees of freedom. Now, when it comes to quantum field theories, of course, where a lattice quantum field theory, one is always dealing with a finite number of degrees of freedom. That's always the case. The continuum limit, of course, is where this is becoming arbitrarily large. But it is going to be the case that we will be performing computations with finite lattice spacings and in finite volumes. So this, in principle, boundary is only going to appear in considerations of how the resources scale as you actually take the continuum limit. And of course, we're all aware of this. It's also the case that d-dimensional systems are optimally simulated with d-dimensional systems. And so if one's interested in three-dimensional quantum field theories, then these are efficiently simulated in principle with three-dimensional quantum simulators, and unfortunately inefficiently in, say, 1D and 2D systems. So that's something that we also have to keep in mind. And the time evolution, the simplest time evolution that we learned about as undergraduates or at high school is Trotter evolution, where one performs a finite time decimation of the evolution operator that one wishes to apply, and then repeatedly applies it. There's, of course, remarkably sophisticated theoretical analyses and developments in how you actually do that at the level of Trotterization, Trotter-Suzuki. And then there's new ideas that have been suggested and are being implemented. For instance, Q-drift, fast forwarding, linear combinations of unitaries, and all of these have advantages. Some of them have disadvantages, but it's important, and of course we're all doing this and checking out how each of these algorithms scales for the problems that we're interested in. And so one of the questions, of course, is in seeking quantum advantages or first quantum advantages in scientific applications. The question then becomes, in this regard, is what is efficient on near-term devices, which is a different question to which are efficient at scale. I'm just checking the time here. Okay. So I need to speed up a little bit, so I will skip this. So when it comes to strong interactions and QCD, then we've actually spent quite a bit of time in Seattle thinking about conformal field theories, and in particular massless non-interacting scalar field theories. And the reason for that is because if you think about QCD at short distances, at very short distances, QCD is massless and near massless fields. There's 8 gluons and 3 light fermions. And so this, it looks like you have, of order 10 or more conformal fields. But then at long distances, it's known you have the pions are the long distance excitations. And so you have, again, massless, approximately non-interacting, nearly massless, approximately non-interacting scalars at long distances. So you have at both ends of the spectrum, long and short distances, you essentially dealing with massless non-interacting fields. As you move through the confinement and chiral symmetry regime, of course, the entanglement structure has to change dramatically because the number of degrees of freedom that are nearly massless and non-interacting is quite different. But nonetheless, there's some transition region. And if you want to, and in thinking about how to set up QCD in particular onto a quantum device, then understanding the entanglement structure is important. And so a first step in doing this, of course, is to look at non-interacting, massless, or scalar field theory, even with a mass. And so I've been working with Natalie Clow and also recently Natalie Clow and Doug Beck on looking at the entanglement structure, particularly the negativity in the vacuum of scalar field theory. And this, of course, builds on a long history of explorations of this kind in quantum information science. I've just listed 3 of the authors, but there are many, many authors that have contributed. And so it was kind of interesting that one of the interesting barriers that we encountered in coming from lattice QCD to think about this was we had to understand that lattice scalar field theory was the same as a harmonic chain. And once that identification was made, then the literature suddenly opened up, which was exciting. So one of the things we've done is we've taken non-interacting massless scalar field theory, latticized, looked at spherical regions and asked what is the distillable entanglement, what is the negativity between these regions. And we've done this in somewhat of a brute force way through explicit numerical computation. In particular, the analytic tools fail as very close to non-zero separation. And so we were really interested in what happens at long distances. And so one finds that the distillable entanglement drops exponentially as a function of the dimensionless quantity R over D. And in one dimension, the scaling of that exponential tends to 2√2, and then in 2 dimensions, it's about 5, and 3 dimensions, about 7. But an important part of this calculation is the fact that as you increase the separation and ask where is the support in field space of the negativity, the support moves increasingly towards the ultraviolet. So in fact, in these systems, as you know, in spin systems, as you separate, there's a death of entanglement that happens where the negativity drops to 0 at some point. And this corresponds to the fact that there's a bound in momentum space that can be supported. So of course, in reality, in physics, there's going to be some new physics that takes over, and there's going to be different degrees of freedom. So one doesn't expect to see a drop and a zeroing out of the negativity or a death of the negativity. One expects to see some modification to its behavior. But the important point here that was quite surprising is that the long distance behavior of the negativity is influenced by the ultraviolet structure of the underlying theory. So again, this is something that we have to keep in mind in simulations. And the recent work that we did with Doug Beck and Natalie was to understand that there are transformations that you can do to transform the modes in the field in such a way that all the entanglement is contained in a few strings with the negativity exponentially distributed on those strings, and then a halo, which is separable, and it's made separable by noise in a way that's analogous to the discussion of the Werner state, but it's entangled. So one of the things that we're really focused on is to use this entanglement structure and this theory to enable more efficient simulations on devices, but we haven't done that yet. I should also mention that there's experimental efforts, particularly using Josephson junctions, that are underway. And one of the exciting parts of this is simulations of lattice conformal field theories. And I'm going to skip this. So quantum field theories 101, what are we really targeting to do here? So we have a finite lattice that supports our fields, expecting 3 dimensions for a 3-dimensional simulation. We're going to do real-time evolution. The fields are mapped onto qubits or qdits, and there is no unique mapping. And at this point in time, there are no winners and no losers when it comes to deciding on how to map. And so all possible mappings are being and are to be explored to understand how they scale. The boundary conditions, again, these are free to choose. It is the case that computations will be hybrid, and so understanding how to separate into the classical versus quantum is important. And of course, at the end of the day, as with any lattice QCD or lattice simulation of fields, observables must be presented with a complete quantification of uncertainties. And so all of the sources of uncertainty systematics that exist in lattice QCD are also present in the simulations that everyone's envisaging for quantum field theory, except there's more now. That is with the discrete Hilbert spaces potentially used to describe the gauge fields, then there's other sources of error in fact, truncating the fields themselves. So as I said, with the mappings, there's 2 mappings that we're pursuing, and many people are pursuing, of course. One is the Jordan-Lee-Preskel mapping for scalar field theories, and another is mapping of such systems onto spin systems. And I show Stefan Kasper and Hirsch Singh here. These are 2 postdocs in Seattle that are working on this. And so one can imagine that with the spin systems, even though it remains to be demonstrated, one expects to be able to map the quantum fields onto spin systems, and with particular renormalization group blocking and scaling, recover the quantum field theories that you are seeking. With the JLP mapping, one places finite dimensional Hilbert spaces on each lattice site in a One of the things that we did a couple of years ago was to consider the classical correlation links in building quantum circuits. And we found that, for instance, over here on the left-hand side, there's a multiply controlled rotation. And for instance, there's circuits that are upper triangular in how one can initialize the ground state of a scalar field theory. if you add redundancy, so you write this multiply controlled gate as a sequence of multiply controlled gates with increasing number, then clearly there's overcounting that's happened here, but it allows you to implement a truncation. And with the exponentially falling classical correlations, one can truncate this series with exponential convergence after some number of implementations of these controlled operations. And so we did a study and showed that, again, for non-interacting, but also discussed how it applies for interacting theories using basically a domain type decomposition, that one can have an exponential ordering of angles. So moving on to the hardware is something that we also looked at, and many of you have also explored, and the hardware will be imperfect forever at some level of precision. Again, the question is, what is the level of precision that you're targeting for your calculation? One of the things that took us a while to really understand at a deep level was the fact that the quantum devices are really quantum many-body systems. I know this sounds like it should be obvious, but when you're intending to apply a single qubit gate, one's actually applying a multiple correlated qubit gate. And the fact that you have a non-trivial communication fabric between qubits in general means that there's correlated crosstalk and correlated interactions. And so one of the things that we found that changed how we did things was the fact that if you apply, for instance, a Hadamard gate in when all the qubits are aligned with are in the ground state in 0, then you have a slightly different gate performance than if there's a wave function supported elsewhere on the chip. And that's demonstrated here. The comparison between the blue and the purple in medium denotes the fact that there's the rest of the chip is in some other wave function when you apply the gate. And so what this meant was that we modified our workflows in such a way that we integrated calibration workflows, particular, targeting specific operations and gates. These were interleaved with the actual physics workflow, and we used sort of an experimentalist's mentality here in providing, post-processing cuts on the performance of the gates and these various calibration circuits before accepting physics results. And I'll skip that, and I will skip that. So the roadmap forward is kind of mind-blowing in the sense that IBM just announced 127 qubit chip, Eagle, that's you can see it on their website, but the plan is for next year to have a 400, and then the year after is a 1000 qubit superconducting qubit device available, which means that we have to start preparing now to perform computations in quantum field theories, for instance, Yang-Mills, at the scale of 1000 qubits, because the next 2 years will fly by, and there's a lot of work and infrastructure that has to be put in place in order to make that manifest. And then so that takes us to 2023, and it's it's never I don't want to say it's never helpful. It's dangerous to extrapolate, but one sees where this curve is going. So there's been some important developments with regard to error correction. So error correction was something that 3 years ago that was not really prominent, at least in our thinking. On the other hand, the results that are coming out are remarkably encouraging. So this year, Google presented a paper where they demonstrated exponential suppression of bit or phase errors using the repetition code. The results shown here on the right curve, and there's also interesting progress coming out of other collaborations, both particularly on the trapped ion systems and including from Honeywell. So the evolution of hardware is something that we've also been thinking about. And so this is adapted from a figure from Google. If you think about the natural evolution of qubits, and I use the word natural in inverted quotes, one sees that because of the thresholds inherent in error correcting codes, there's a real drive to reduce the uncertainties and the error rates in single qubit operations. And then once you blow the threshold, quite significantly below the threshold, then one can increase the number of identical qubits, for instance, that gets integrated together to form a logical qubit with the surface code, and exponentially drive down the errors in the logical qubits as you increase the size of the surface code. And so if you think about devices one might use for science, then certainly there'll be commodity devices that are available to solve, or at least start addressing, all of the problems that you're interested in principle. But it's also the case that one can imagine designer devices where the particular physics would dictate which pieces you need of the problem you need to solve precisely, and which can be solved with larger uncertainties and still reach the target. And so as a result, while there's going to be commodity devices, there's certainly strong motivation to develop and co-design devices for particular scientific objectives. And so that's what's indicated here in the right plot. And this was a figure that you can find in this article that Natalie Clough and Alessandro and I wrote. Okay, so yeah, I'm going to take 5 more minutes if that's okay with the organizers. So the Schwinger model really started at this area to a large degree in 2016. Work by Christine Muschig and others at Innsbruck performed the first calculation in the Schwinger model of dynamical evolution of a quantum field theory. With 4 qubits, they showed pairs popping in and out of the vacuum. And that was sort of a sea-changing moment, at least when I read that paper. And so since then, there's been a number of efforts internationally looking at this model. It's a really important model to explore because it shares features of QCD. It has charge screening, and the ground state has a non-zero fermion condensate. It also has bound states of hadrons. There's a 2-body bound state and a 3-body bound state. And so in addition to the time evolution of pairs now that exists on multiple devices, there's been also some other aspects of this examined. So for instance, a non-zero theta term, there's been work coming out of Brookhaven where one changes the value of theta and then asks, what does the currents do? And so this is results from a simulator. And so one sees that one is able to compute, at least on a simulator and also on devices, what happens as you perform a quench. And it's also the case that at finite theta in Euclidean space, there's a sign problem. And so this other group out of Brookhaven was able to show that in this model with a non-zero theta, with a quantum device, one is able to address the ground state effectively. I'm going to skip that. And there's been activity in non-abelian gauge theories, both in issue 2 and issue 3. So let me just summarize in issue 2. There's sort of a one-dimensional chain of plaquettes and the time evolution of gluons coming in and out of the trivial vacuums being performed. And there's a number of lessons in here. So this was Natalie Clough, Jesse Stryker, and myself. There's been work on quantum annealer. So this is work by Randy Lewis and collaborators, where they used the Feynman clock on the D-Wave devices to extract the time evolution of the chain of issue 2 plaquettes. And so this was also one of those moments I didn't really quite understand the utility of an annealer for time evolution, but this work, which was built upon Google's work in quantum chemistry, was a clear demonstration. And there's also work by Christine Muschig and Randy and collaborators of looking at the ground state of a one-dimensional chain of issue 2 also, and also extracting the particle masses. So this is also very, very nice work. So Yang-Mills in general, the general scheme for performing such quantum simulations was outlined in this paper in 2006 by Burns and Yamamoto, truly a forward-looking paper. And the Hamiltonian is the Kogut-Susskind Hamiltonian. It's simple to write down. And one discretizes it or maps it onto a lattice using a finite dimensional Hilbert space associated with each link. And one can arrange things in such a way that the location in the Hilbert space indicates the dimensionality of the QCD irrep. And so at the end of the day, one has a wave function for this entire system built upon entangled combinations of all of the links on your lattice, which is then written in terms of the QCD irreps up to some cutoff plus the alignment in the gauge space at each of the grid sites. Now, it turns out that Klebs-Gordons can be evaluated efficiently on a quantum device. This was shown by Bacon, Chung, and Harrow in 2006. And Gauss's law is unfortunately enforced by hand. Has been a lot of work recently of a number of groups internationally understanding how to have Gauss's law be sort of softly preserved dynamically through adding terms to the Hamiltonian, and these look very promising. So let me skip that because I've said that. And so we performed calculations of a single issue 3 plaquette on IBM's systems earlier in the year. And so here there's again a trade-off between the size of the trotter step, the quality of the order of the trotter evolution, and so forth. But we're able to provide initial benchmarks for instance, the expectation value of the Hamiltonian at some time in the evolution that can be used to calibrate subsequent quantum simulations. The circuit is very simple and of course can be made arbitrarily complex as you increase the precision on the theory side. This was also extended to 2 plaquettes with some lessons that I will not talk about. So my second to last slide, errors. So in any of these quantum simulations, of course, one has to worry about error correction. It's certainly the case that qubits will flip and dephase and so forth. And so from a theoretical point of view, it's important for us to understand what they would look like in our simulation. And so, for instance, for a Yang-Mills calculation, where one has quantum registers and qubits defining the Hilbert space on each of the links, then you can imagine, for instance, say a bit flip will just change the irrep of the color group. And so what that means is effectively, in most instances, this will mean that you have a violation of Gauss's law at each of the vertices. And effectively, there's a color charge and an anti-charge located on adjacent lattice sites. Now, one of the great things about Yang-Mills is that it's confining. So under subsequent time evolutions, in some of the instances, one can imagine, under subsequent time evolutions, because of confinement, these errors are not going to move far away from each other. Whereas in U1 theory, in 3 dimensions, these will drift apart. But with the confining theory, they're going to be confined within the confinement radius and therefore easier to find when it comes to error correction. And this has been utilized and exploited and there's a initial paper in 2015 by Bomben and subsequent works related to this. So I'm going to skip that and close. So we're in a remarkable period. We're seeing the emergence of quantum mechanics 2.0 with control of entanglement and coherence. And of course, dramatic implications for computing, simulation, communication, and sensing. And we're starting down the road for quantum simulations of standard model physics. And it's a remarkably exciting period. So thank you very much.
Thank you very much, Martin, for this very inspiring talk. So we would take questions now. There is still some time for a discussion, so you can write them in the chat or open up your mic and okay, then I will start with a very general question, which is at the beginning of your talk, you say that we don't know which I mean, in which cases quantum computer will solve or will not solve a sign problem. So naively, I would expect that in principle, they could solve all of them. But maybe I'm missing something. So do you have any, so what would be something that we cannot solve given a universal quantum computer, perfect and scalable and so on, of course?
Yeah, that's right. Yeah, we're all assuming perfection here in most of these discussions. So for instance, so finding the ground state, for instance, of a general Hamiltonian with in-body interactions is not efficient on a quantum device. So for instance, the planeless effective field theory nominally between nucleons with even just two-body interactions, but even three-body is something that for a general set of couplings is not efficient on a quantum computer. On the other hand, there's been great progress in solving these problems because one can solve something that's perturbatively close. And so you're solving a slightly different theory in a way where one can systematically correct and get within the precision desired to where you want to go. So that's why that discussion I feel is quite important, because things that in principle, with infinite precision, you're in the wrong complexity class, but for any practical purposes, for the precisions that are going to be required now and far into the future, in fact, they can be done on a quantum device. So that's what I was sort of getting at. But it's not clear that that all problems will, I think it's certainly clear that most problems don't sit in BQP.
Nice. Thank you. So again, any question from the audience? Then I will go with my second one, which is related to one of your work that you have seen when you compute the logarithmic negativity of the quantum field theory in 1 to 3D. So I just wanted to ask you, I mean, how actually do you do that? So what kind of calculations have you done over there? You were very fast on that.
Yeah, okay. Yeah, so again, there's been some really nice, I mean, the last 20 years of work by the QAS community has been, on continuous variable systems has been, has enabled this. So you have the system and you're taking regions of the vacuum, and then you can calculate the covariance matrix by looking at the 2-point function from, point X to point Y, multiplied by the 2-point function of the conjugate momentum from Y to Z. And so you basically, you can form the covariance, the 2-point function for phi. There's some matrix which takes you between all points in these extracted regions. And then there's the 2-point function for the conjugate momentum. And, you can, and again, results from continuous variable systems, multiplying these together with a partial transpose, and then finding eigenvalues is basically the mechanics of that process. So that's why it's somewhat brute force. The complication in these calculations is that the correlation functions are either logarithmic in 1D, for instance, or polynomial, and the polynomial in higher dimension. But you're looking for something that's exponentially small. And so you have a exponentially poorly conditioned matrix that you have to then diagonalize. And so the complexity, and that's why these error bars, as you increase the dimension, these error bars grow, because you have a dimensionality of a matrix which grows not sort of as a bit smaller than you would guess, but it still grows as you increase the number of dimensions, and you have to deal with an exponentially poorly conditioned matrix. There's tricks. So in 3D, for instance, you work with A1 irreps in the transverse direction, and you can store those to disk and pull them out of disk and use them. But I would say that our approach is, and this is not saying negative things about anybody, but kind of brute force and unsophisticated. But we so far don't know of a better way to deal with this problem. The entanglement Hamiltonian is clearly something, if you could get under control, then this would solve this problem likely quite well, but we haven't been able to do that yet.
Thank you very much. And here comes one question from Peter M. Does it take much difference on the hardware? For example, superconducting ion traps, neutral atoms, etc. I think to implement those simulations is meant.
The simulations? Oh, so yeah, so the resource estimates for performing the calculations, for instance, of Yang-Mills are at early stages. So for instance, just describing, for instance, a link, one single link using the Burns-Yamamoto basis requires 16 and probably for error correction, 18 qubits. If you truncate, if you only keep the error reps of 1, 3, 3 bar, and 8. So even for a fairly low cutoff, the quantum numbers that you have to keep describing the orientations of both ends and the entanglement between them and the color error rep is substantial. Now you can use gauge invariance. So this was a trick that was suggested by Murray Kammer-Barnwell, Carl Janssen, and others, and we used in our SU2 calculation. You can integrate out using local gauge invariance each of the grid points and perform a simulation just in terms of the dimensionality of the error reps. And so in which case then the dimensionality then of that link variable in the simulation drops down to just 2 qubits. So you can shrink 18 to 2, probably at the expense of being able to do error correction on the ends, but we'll come back to that at some point. As far as the circuits goes, we're in the process of really building circuits for Yang-Mills, Burns-Yamamoto, and while we have an idea for the scaling, it's not final.
Great, thank you. I think our time is ending. If there are no other urgent questions from the audience, I would thank again Martin for this talk and for his time. Thank you very much.
Thank you. Yeah, thank you very much for the invitation.
And Simone?
Yeah, Raffaella, are there, if you can put on the slide for an announcement of the next year. So there's no actually, the program is not yet fixed, but we will announce it. So we will keep on next year with this series of Quantep seminars, and we will move them to the second Wednesday of every month. And soon you will find our website, and our mailing list will announce the speakers for next month. Let me ending the session, thanking again, of course, all the scientific organizers, the local organizers that make this thing possible, Raffaella and Sagar, and of course the funding, European funding that funds our project. Thank you very much. Goodbye.
Thank you.